Welcome to the Power System Protection course. We are continuing with travelling wave based protection. In this lecture, we will address on application of travelling waves for protection perspective, two relays principle, line differential and directional relay for line protection. We have already seen in the earlier lecture how to extract travelling wave and how they can be explored for possible application. In this one, we will see these two specific applications. Let us come that to revisit on the scope of travelling wave. So, we have already seen that the travelling wave goes towards the line end to the relay location at a speed of almost speed of light, the gamma, which depends upon 1 upon root over of L C. These two relays are available by vendors in the market, travelling wave 32 directional relay and travelling wave 87 line differential. At this speed perspective, they can decision within 2 to 3 milliseconds. Of course, that depends upon the length of the line. We will see that. This technology is evolving, even though the concept is pretty old. To realize that is tougher. We have already addressed in last lecture. It is associated with high frequency component. So, sampling rate is requirement is very high. So, associated technology is also much better than the conventional 3 to 10 kilohertz sampling rate based relay. This technology is moving forward, evolving. So, in near future we will see more and more applications based on travelling wave principles. On signals, we have also mentioned earlier that these are high frequency transients. CT bandwidth is compatible for extracting the current based signals for possible application, but on CVT, if you see the CVT, then because of you can say that the inductor, the associated you can say that voltage gets inhibit, and then you can say that we may not get the proper voltage signal of the system. However, the fast wave literature suggests is available because of the stray capacitance of this inductor and the corresponding transformer in the associated with the electromagnetic unit. So, this gives a scope to reach the corresponding relay site about the initial voltage transient. Afterwards, the voltage gets distorted and it is difficult to extract the corresponding system side transient voltage associated with the travelling wave. A typical some of the specification of a travelling wave relay is that sampling rate is 1 megahertz as compared to few kilohertz for the conventional phasor based relays. The ADC A to D conversion is typically of 18 bits, we require more accuracy, 12 bits or so for normal relay. Anti-aliasing filter, the cutoff frequency is 400 kilohertz associated with the 1 megahertz sampling rate. Now, let us come to these applications on the travelling wave line differential TW87. So, conventional line differential we have seen how both the ends currents can be used, both sample domain as well as phasor domain. Similarly, here also we will see how current based travelling waves how they can be used for differential principle for possible applications to protection. Already mentioned, such a travelling wave based approach gives high speed protection. It is current based, and because the associated signal with travelling wave remains for very small period, millisecond and or so. So, therefore, we see that the protection scheme has to carry out pretty fast, and the decision is obviously much faster than conventional relay. So, it requires point to point fiber optic channel for application, and the decision time you can say that for in zone faults is around 1 to 5 millisecond only, whereas in case of phasor based approach and so typically it is a requirement of half cycle and more. These travelling waves are sharp changes in the input signals. Whenever a fault is incepted, the travelling wave propagates towards the line ends, where through the protection arrangement such signals are being captured. Note that in last lecture we have mentioned these are not 50 hertz signal, these are high frequency components. So, we have different steps to capture that information using band pass filter and so. Also we require that alpha beta transformation perspective. Now, this rise time of the signal is of the order of few microsecond only. The relay runs the travelling wave calculations every microsecond, 1 megahertz sampling rate, and the associated logic protection principle can be managed with every 100 microsecond and so. So, what we do here in this travelling wave based line differential, that let us say an internal fault happens to be there at f 1. So, current waves will travel both m n and n n. So, here with the CT and the A to D process, the relay will acquire the samples value, filter out the undesired component, capture the high frequency component, and then extract the alpha, beta or like that whatever components required, and then you can say that based on that a differential principle can be obtained. So, the travelling wave quantities, the I cap, m and n are the extracted frequency extracted current components, the high frequency component which we call as travelling wave components, and they are obtained from the sample value of I m and I n, and these are sampled at a very high sampling rate. Now, let us go to how this travelling wave based differential protection is being applied. The differential relay uses, this is one of the application perspective. There are different ways you can see in future also. Differential relay uses peak values of current travelling waves of both sides. So, the relay, the line which we are considering this M N line, and our relays are R M N and R N M, travelling wave based relay T W 87. So, from the samples value at this location and this location, they obtain the travelling wave components as shown here, and they exchange the corresponding information through dedicated fiber optic cable. So, what they use is the peak value of the travelling waves. So, what I do here is step 1, compare the operating and steering travelling wave quantities. Travelling wave quantities are we mentioned in terms of I cap. So, I operating equals to I m side peak value plus I n side peak value and magnitude of that. Restraining quantities is I m side peak value minus I n side peak value magnitude of that. So, what is this MP and NP correspond? They are the peaks of the fast wave. So, when you consider the fault is incepted, the wave travels this side and this side current wave, and it is captured by the consider the relay at this Mn and the Nm. So, we plot these two on the time axis, same time axis. Then the first wave is the black one, this one at the M end, and the red one you can say that is the first wave captured at the N end. So, that is why this is travelling wave at bus M and travelling at bus N, red one. And then this you can say that first wave is of concern, and the subsequent wave we are not considering here. Note that the travelling waves, because of the attenuation, the signal strength dies down, and subsequent you can say that at stages they may not be, the relay may not be able to distinguish you can say this because of noise and other factors. So, it is reliable you can say that we can use the first travelling wave, and that is why I am talking about this peak value of this. So, this travelling wave, and again you can say that the duration of this is few microseconds. So, every detail of you can say that this one to compare them is also not that easy. So, what is being done that one approach as mentioned here, either take the peak values and use these you can say thus for the operating and discharging signal. So, IMP and INP are the peak values of this first wave at M and N end respectively. So, we obtain this I operating and I discharging as shown here, and then check for internal fault whether I operating is greater than I discharging, like we did for the differential protection. But note that these signals are available only for few microsecond and very quick processing aspect is done. So, to make it more secure, there are other two checks a typical relay use. It may incorporate more also you can say that for better decision. Two checks are, the next step 2 is the directionality. For this you can say that the direction information is extracted from the polarity of the signal. If both you can say that polarity of the signal are same, either positive positive or negative negative, then it ensures that you can say that the directionality is same, and then it is internal. Now, when you can say that the what you mean to say here that when the travelling waves goes this side, so if it is a positive you can say that wave, current wave, and reaches here, but the relay sees you can say that towards the this side. See, if you remember or you can say that in phasor domain approach or simple domain approach, what we are saying that for this fault this source was feeding from this, and for this same fault this source was feeding from this. So, our relays we can say that looking at the forward you can say direction to the line in this panel to identify the internal fault. So, here what happens, the wave propagates positive wave you can say propagates this way. So, that is against the conventional direction of this. So, if we consider that as the negative, then for this side also that all becomes negative. So, both are negative and negative, and if the wave is generated here is a negative you can say that signal, then both will be positive or positive. So, that is what we say the direction of the at the you can say that M N N for the current wave originating from the fault F 1. This is situation for internal fault. What we are discussing is for internal fault. So, in the next check, the security check for differential protection using travelling wave, we have a fault location based check. We are discussing on internal faults. So, let us see that this F 1 position is the internal fault within the line M n. So, whenever such a fault happens to be there, current wave will traverse left hand side and right hand side. So, if you see this space time diagram, lattice diagram, then the wave which traverses this path distance of d, we will take a time of let us say T m to reach this relay location R m n, and this distance L minus d to the right to bus n, it takes let us T n. So, this T m equals to distance d upon the gamma, the velocity of propagation, and this T n time is L minus d upon gamma, the propagation time. So, d being the fall location from bus m n location, from bus m, this is the d distance, L is the capital L is the line length of the m n section in kilometer, and gamma is 1 upon root over L c, the propagation velocity. Note the T m and T n are the fast travelling wave arriving at bus m and bus n respectively. Now, from these two relations we can say that the d will be equals to half L minus T n minus T m into gamma. So, these two equations reveal the distance d equals to half L minus T n minus T m into gamma. Now, these devices at m and n record the arrival times, let us say T m dash equals to T m plus T naught, where T naught is the fall inception time. So, there is a time at which fall is being incepted, and then it traverses this one. So, the recording time at R m n by the R m n relay is T m plus T naught, and that equals to let us say T m dash as recorded at by R m n. Similarly, at the n side T n dash equals to T n minus T naught, T n is the travel time plus T naught is the fall inception time. So, now assuming that both end data perfectly being synchronized, clocks here R m n and R n m being perfectly synchronized, then the T n minus T m equals to T n dash minus T m dash, T naught cancels out. So, we got T n minus T m equals to T n dash T n dash. So, in this relation we can obtain the recorded time at m and n end, and from there you can find out T n minus T m as here, and from that relations L and gamma are already known from the system. So, therefore, d can be obtained. So, for an internal fall the d should be less than L or d by L should be less than 1. So, once you ensure that from this relation using the time information at m and n end, we can compute the d and ensure that the fault is internal or not. Now, let us go to the external fault case. So, for this line external fault F 2 is there this side or it can be this side. Let us consider for this F 2 fault and the associated travelling wave captured here from the sample value of I m and I n. So, for differential relay we will first obtain the I operating and the I restraining from the I cap m p plus I cap n p travelling a peak value, first peak value at m and first peak value at end n, and the restraining you can say that is I m p minus I n p magnitude of this. So, for external fault we see you can see that here that this I m p and this first peak at the m end, the black one is m end and the red one is m n end. You see here this is positive and this is negative. So, this plus this will be less now as compared to the I restraining this minus this. So, when you did this minus this that will be added, and when you make this plus this that will be lesser. So, therefore, you can say that I operating become less than I restraining for then external fault case as evident from the wave also. And for you can say that the check security perspective as you did for the internal fault case. So, for external fault case what we see here that the positive peak we can say that for this case is positive and the other one negative. So, they will be not of same sign, they will be not of opposite sign, and this you can say that plus minus or minus plus for m n n n and the other way. So, what you see here that for this fault, if this current wave let us say positive one propagates this way. So, this you can say that for this case this will be along this one. So, if this will be positive, for this one it will be against this one as per the conventional direction. So, therefore, you can say that this will be negative. So, this will be positive and negative, and if the corresponding wave is negative wave, then this will be negative here and positive here. So, negative positive here. So, therefore, the direction of you can say a conclusion can be obtained from you can say that the peak value of the first peak value of the travelling wave obtained at the two locations, and that you can say that indicates about the external fault situation. Unlike for internal fault, we see both polarities are same. Similar to the internal fault, for external fault also we can have this security check on based on the fault location. Now, it is a case of external fault and how the corresponding location is related to for the differential protection. So, for this protection of the line section M n, this fault is an external fault F 2, and in this case the distance of this fault from bus M is d dash. So, whenever the corresponding travelling wave reaches at bus M from this fault location, then the corresponding time associated with that becomes T m from the lattice diagram. So, travelling wave goes T m. Now, that traverses through this line M n and reaches at n at T n. So, the time difference between T n and T m is nothing but this corresponding space distance is L. So, this T m equals to d dash upon gamma and T n equals to L plus d dash upon gamma, velocity of propagation for line section M L and M n to be same, assuming to be same. So, therefore, T n minus T m, T n this portion minus T m that corresponds to the space L. So, L upon gamma the velocity of propagation that equals to tau. So, we see that if the fault happens to be left of M at any point, then the time recorded at M T m and the T n at M and n buses difference will be L upon gamma, that is equal to tau, where tau is the propagation time for the line section M n by the wave. Note again, like the internal fault case, T m and T n are the first travelling wave arrival at bus M and n respectively. For external fault beyond line section beyond the bus n to the right, we can similarly say that from that the corresponding fault inception will be there and reach at n first and then goes to bus m. So, therefore, we can conclude fault for right of this n will be equals to T m minus T n will be equals to L upon gamma, and that equals to again tau. So, in general we say that for external fault left of m or right of n will be equals to the mod of T n minus T m will be equals to tau. So, similar to the internal fault case, we have a third check, the security check on external fault, which we find here that T n minus T m equals to tau. But this T n and T m like the earlier can be computed from the recorded time by the R m n and the R n m relay following the fault inceptions at T naught, and that equals to the recorded time will be T m dash minus T n dash will be T n minus T n. From the recording time and using the relations T m minus T n equals to T m dash minus T n dash, this will be equals to, if it is equals to gamma, it ensures that the fault is external beyond the line section M n. Summary: for a trip decision, when to trip for any internal fault in the line M n, trip you can say this, the I operating should be I greater than I disturning. If not so, then it is external fault. both end travelling wave polarity should be same. This is check, first check, both end travelling wave polarity should be same, either plus plus or minus minus. And the third check, we can say that the magnitude of T n minus T m is not equals to tau. If it is equals to tau, probably it is an external fault, and then we check as already mentioned for internal fault. If this is not so, then D must be less than L or D upon L should be less than 1. So, with this we can say that we can say that the travelling wave based can take a correct decision based on the differential principle I operating greater than I restraining, and these are the two checks. Let us see example. First example on travelling wave based differential protection. So, this is an internal fault case 50 kilometers from bus M for this 200 kilometer line. Now, in this case we see the gamma given based on the LC parameter considered for this one transient simulation package using this. Phase A current at both the ends M n and N n, and note that our focus will be only this portion where the transient is being initiated, this portion, because that is the surge being injected to the system, and that is our travelling wave, and this is few 1 to milliseconds only for which our observation should focus on. Now, if we expand this portion, then this become, you can say that the black one you can say that is M n and the red one is N n, and you see you can say that this is almost DC. So, we are talking about this portion only, this whole you can say that is sinusoidal one, from which we capture the fundamental using the phasor and so in the earlier discussion on conventional relays. But now, you can say that our focus is only this surge, you can say that this change. If you see this change, you can say that that is our concern point. So, the first peak you can say that here, and for the M n and for the N n you can say that this. So, this leads to you can say that our conclusion, and we extract from this you can say that portion the high frequency component. So, this is positive, this is a negative, and so also the red one is negative, and our focus is for the differential the first peaks at M n and N n, black and the red respectively. So, the first peak you can say that gives us you can say that often at 171 millisecond as recorded, and that you can say is minus 838 ampere, and this one is minus 236 ampere. So, we will calculate from this as step 1 for the differential principle operating current, addition of these two you can say that first peaks. So, this is minus 838 minus 236. So, this mod of this gives you 1074, and the restraining one IMP minus INP, the travelling wave part, that equals to minus 838 minus of 236 gives you 602. So, we clearly see you can say that the I operating is greater than I restraining. So, this check satisfies that this is a case of internal fault, and this of course, is in agreement with the simulation situation. Now, we will go to the check first. The first check you can say that on that directionality to support the corresponding thing for a secure decision directionality. We see both you can say that waves are positive and positive or negative and negative, that was the requirement. So, here you see that both you can say that first waves are negative polarity, and that is what we say, and we have already explained that. So, here you can say that both polarities are. So, this is also in agreement with the internal fault situation. The third check is on fault location. So, here you can say that we calculate D equals to half L minus T n minus T m gamma. So, this equals to 0.5, L is 200 kilometer line length, and then you can say that we have this corresponding T n and T m 516 minus 171, and then you can say that we have microsecond 10 to the minus 6, and this is your gamma value is given, you can say that already given to us based on the LC parameter of the line. So, this calculation gives us 50.14 kilometer. So, from this M n, and that you can say less than 200 kilometer. So, that are the second check also in agreement with that this is an internal fault. So, this ensures that the conclusion is that the I operating is greater than I restraining, that we have seen differential agreement, and for security check we say they can say that the direction is same both negative polarities, and also you can say that D is less than L. So, it ensures that there is an internal fault, and we have simulated this case also for phase A to ground fault at 50 km from this. So, this calculation check obtained from you can say that the two relay locations from the travelling wave ensures so that. Thus, the TW 87 functions correctly for this case. Example 2 is on second situation, and that is an external fault case. So, beyond the line towards the left of M and between M and L. This is created 50 kilometers from this M bus, and the corresponding signal obtained you can say for phase A is this, and then you can say that we have if we expand this, you can say that again we are getting like this. So, this is our focus, this change you can say that which you observe, the first change which we observe in this case. Now, coming to this, we see here you can say that the corresponding wave at the M end you can say that it becomes positive because it is coming from this side as already explained, and for this N end you can say that this becomes negative, and that is what you observe, you can say that the positive peak and the corresponding negative you can say peak. So, the first peak you can say that two are of opposite sign. So, that sign also says you can say that they are not internal, they are external. Now, let us see I operating what it says. I operating you can say that becomes equals to 572 if you substitute these two value plus and minus, they reduce the value, and I standing you can say that is magnified. So, that is you can say that 964. So, you see you can say that I standing is greater than I operating, and that clearly says that it fails in the first principle of differential principle. The other checks are to confirm it, confirm that you can say that external fault case, we see the polarity positive and negative, and that see that the directions are of opposite sign. So, that means that this is external, and the subsequent check for distance you can say that calculation gamma given and tau L by gamma is 692 microsecond for this case. So, T n minus T m is 863 minus 172 is 692 which is equals to tau. So, we have seen you can say that as per our external fault case, the magnitude of T n minus T m should be gamma, it should be tau, where tau which you can say that is L upon gamma. So, that you can say that is the situation. So, in conclusion we say that I operating less than I restating, polarities are in opposite direction, the direction of travelling wave is opposite also, fault location you can say that is equal to the line length or the time you can say difference T n minus T m magnitude you can say that is gamma. So, this clearly you can just say external fault case. So, we see that you can say that how travelling wave principle can be applied to differential line differential protection applications. Now, on the speed perspective, how fast TW87 best protection. Now, let us in this slide we will try to see that what will be the time frame on decision perspective, because we are mentioning about only few milliseconds only. 200 kilometer line same one, and then you can say that the travel fault happens to be somewhere midway and it travels this side and that side exactly at 100 kilometers. So, that is why it takes 346 millisecond this side microsecond and 346 microsecond this side. Once this reaches this end, let us say our all calculations are based on m end at this purpose, similar calculation they are at the n end also. So, at this you can say that point it takes 100 microsecond to process the signal and then sends to the fiber optic cable in a time of 1 millisecond. This is the communication time 1 microsecond, T c for communication time, P n for the processing time at the n end, and then you can say that we require further you can say that at m end further processing time of 100 microsecond. Already mentioned in our diagram also that the corresponding travelling time is every microsecond it captures the signal, but every 100 microsecond or so you can say that it processes the corresponding principle. So, to apply the principle you can say that it takes 100 microsecond time thing. So, this is the processing time n n and m n. So, in total if you see the time frame of calculations, we see you can say that this travelling time to this end, you can sum up this end travelling time to this end plus this and plus this and plus this. So, again you can say that this time T m minus T n or T n minus T m is required. So, if the fall happens to be, you can say that let us say at this close to consider m boss n, then the travelling time from this to this will be almost that of the line length, that is tau. So, that is the maximum time it will require to reach here, then plus this and then plus this and then plus this. So, this is what you can say that maximum it will take 692 millisecond to reach here to the NN, and then this 100 and then this 1000, there is 1 millisecond communication time, and then the local you can say 100 microsecond. So, this is the total time maximum which you can say that the relay might take for decisions. So, that is why I can say that we say here travelling waves available time. So, the travelling wave reaches you can say the maximum of Tm and Tn. So, that is you can say that we are talking about here, and then you can say that the similar calculation will be done at the Nn also. So, it will be received from this side to this side, and both the ends you can say that relay you can say that should trip the corresponding breaker. So, that is why we are talking about the maximum of Tm and Tn in a traffic process. But maximum I am say that in a time frame what consider the relay is expected to decide will be tau, the propagation time, which happens to be 692, that depends upon L upon gamma. The relay processing time at bus M is TPM is 100, processing time for N at side is 100 microsecond, communication latency T 1 millisecond, there is 1000 microsecond. So, tripping time expected you can say that is the line propagation time. This is what the maximum we are considering in this case just for a typical value. Relay processing time at both ends TPM and TPN, and the plus consider the TC. So, we will be adding all this, we got to consider 1892 microsecond, or that is 1.92892 millisecond maximum. Why maximum? Because you are talking about tau here, but we expected to consider it may take less time depending on the max value of Tm and Tm or Tn, this side or that side. So, the tripping time depends on the line length and the communication latency and the corresponding fault position and so. In general, signal available time depends on fault position, the IID processing time and communication latency may vary based on the selected hardware, communication channel and so. So, that we see here this less than 2 millisecond depending upon the line 200 kilometer and so, and if the line length is larger you can say that it might take 4 millisecond to 5 millisecond kind of thing expected. That shows that how fast is the TW87. Directional element TW32 in a similar perspective, this considers both voltage and current signals. So, for forward event the two travelling waves Vn and Im or Vn and In at both locations. So, these are you can say individual location will check the direction forward or reverse just like any directional relay. Are opposite the forward event you can say that are opposite polarity plus minus or minus plus for forward thing. Forward means this relay looks forward to this side and this relay look forward to this one. So, Vm Im will be of opposite sign, and for reverse event you can say that Vm Im will be of same sign. Now, why? Let us consider the as already mentioned this current internal fault case, the current wave propagates this way and this way travelling wave. So, at this point this wave will be seen as a negative value and this wave will also be seen as a negative value, but associated the voltage will be positive, current is positive, voltage will be also positive. So, voltage will be seen as positive here, current due to direction will be seen as negative, but voltage will be positive. So, that is why positive negative combination here, and similarly voltage here also positive, current negative. So, voltage positive negative. For this fault the current goes like this. So, at this point this corresponding current becomes positive, voltage also positive, and at this point current is negative and voltage is positive. So, you see here you can say that for this case the fault you can say that is reverse, and for this case you can say fault is forward. So, forward fault for forward fault the corresponding Vm and Im for this one will be positive and negative. The corresponding Vm and Im at this point will be positive negative, and Vn and In will be both positive. So, this the corresponding this fault is a forward fault you can say that for Im side and reverse fault for In side. So, Im will see in this case positive negative, and For this case you can say that this one will see both positive positive. So, that is the results you can say that our conclusion is that for forward event you can say that polarity will be of opposite one voltage current, and for reverse event it will be both positive positive or negative negative. Let us see how we can see through examples. So, this is the case 400 kV 200 km, same one what we see for the differential protection. Two situations. First, let us say external fault F2. For this external fault F2, as already mentioned, the travelling wave propagates goes toward this side, relay IM captures, and then relay IN this side also will capture. We have only considered for IM for clarity. For this F2, the corresponding current wave is the voltage wave is positive and current wave is also positive. This is going like this. So, current will also see positive and voltage also positive, both positive and positive. So, that is what we say the positive and positive for this is for reverse fault. F1 is a forward fault, internal fault. You see here the voltage wave is positive and current is negative. For this fault, current travels this way, voltage travels this way. So, it is in opposite direction to the current direction. So, this is negative, voltage will be positive. So, the conclusion that the principle of travelling wave based directional is that for forward fault this side voltage positive, current negative, and if voltage is negative, associated current will be negative, and then you can say that from this side this will be positive. For reverse fault like F2, you see here both are positive, and if voltage and currents with a negative sign travel, so this will be negative, so also this will be negative. So, same polarity means of the first wave, it means that these are reverse fault, opposite polarity means forward fault. This for the first week. Transfer T can be realized, we can transfer the corresponding information trip like we did for this distance relay applications PUTT, PUTT, DUTT and so. Very fast stripping can be obtained with dedicated communication system. Uses both voltage and current. So, we know the limitation of voltage signal and so, but however, fast wave is available. So, in overall we see that the advantages of high speed tripping using the travelling wave approach less than 2 millisecond for TW32 directional line, less than 4 millisecond for TW87, because the relay signal has to reach the other end and processing time is there, we reach both end signals. But here you can say that TW32 requires only one end signal, both voltage and current. Here it requires only current signal. Unlike distance relay, differential relay and directional relay, you will see in case of conventional phasor based approach, it requires very minimum settings. Travelling based method will work for all types of transmission line including series compensation line. For series compensation, the omega, the corresponding associated x 1 upon c omega, omega a high frequency, this is transient wave. So, therefore, the corresponding x for that level of frequency 1 megahertz or so, this becomes pretty small. So, therefore, the corresponding series part, series compensation part will be seen as a shorted path series, and therefore, no reflection or no refraction from there, and that results in you can say that the travelling wave based approach which we discuss about differential direction principle will not be affected by the presence of series compensation even at the middle of the line or so. But these you can say that limitation of the travelling wave, CT allows measuring currents travelling waves true in the required range of frequency, but CCVT has limitations in terms of performance of travelling wave measurement. It requires special measurement device to capture voltage travelling waves if it require the subsequent waves with sufficient strength. Signal strength depends upon the switching instant. Then there is a question. Sensitive to noise, requires high sampling, processing capability and communication bandwidth. So, overall remark for the travelling wave approach, high speed protection is achievable. We saw two applications, difference in the directional. We saw also that how the distance of fault can be calculated, and using that distance relay can be also explored. Travelling wave differential scheme incorporates a built-in fault type identification logic based on travelling waves to support single port tripping applications also. This can be extended to single port tripping also. More applications are today being envisaged. Relays with integrated approach are available, travelling wave, phasor, time domain and so. In case of travelling wave, signal is not available because of the issue, you can say that the low signal strength for certain switching instant, then that should incorporate also phasor also, and there are other reasons you can say that to support that, including time domain approach based on the sample values. So, this technology is evolving and more promising techniques principles are expected in near future. Thank you.